Hello, in this video, we present Visuo-Tactile Transformers or VTT for manipulation. VTT is a novel latent representation learning method motivated by reinforcement learning in real-world robotic manipulation. As we discussed in the related works section of our paper, RL algorithms can be sample inefficient and numerically unstable because they learn from high-dimensional inputs like image. In order to produce a more compact latent space for RL, VTT leverages the complementary nature of vision and touch. What sets VTT apart from other visual-tactile approach is that it spatially distributes visual attention according to tactile cues. The method we present extends the visual transformer architecture and makes three simple assumptions. Firstly, that we provide RGB image as visual input. Secondly, we provide 6-DoF force, torque, feedback at wrist as tactile input. And finally, that all interactions are rigid body interactions. Now we'll give an overview of the VTT architecture. Firstly, we patch and embed the input RGB image with a 2D convolution layer. Then we isolate the reaction force and torque from the tactile input and embed this information with a linear projection. Next, we introduce the alignment and the contact embeddings to enable VTT to build the correlation between vision and tactile modalities under different context scenarios. The learnable modality and position embedding relates modality information to the alignment and the contact embeddings and the modality patches. Then we send all the embeddings into the structure of the transformer encoder to form self and cross attention. A full derivation can be found in our paper. The alignment and contact heads predict the alignment and contact state of the system and are used to form the VTT loss. Finally, the fused heads are compressed by an MLP to formulate the final latent representation Z. This representation is used for reinforcement learning. To evaluate our approach, we conducted 4 simulated tasks and 1 real-world task using an RL agent trained with learned representation from VTT. We benchmarked our approach to 2 state-of-the-art multimodality representation learning frameworks, concatenation and products of expert. The result of our experiments show that in simulation VTT achieves higher sample efficiency in all tasks and a higher success rate in all but the peg insertion task, where it achieves a comparable success rate to the products of experts baseline. In the real-world task, VTT outperforms both baselines. Here, we visualize the latent representation as attention maps overlaid on RGB inputs. In the door open task, we can see that in the beginning of training, attention is not focused on information that is relevant to completing the task, but that by the end of training, attention is focused on visual information that is associated with tactile cues from contacting the door. In the pushing task, we can see that in addition to the cross-model attention displayed, the self-attention is able to focus on the goal states as well. Furthermore, we found that this phenomenon persists in the real-world task. We can see that over training iterations, the attention focuses on task-relevant information. Thank you for your attention.